a few different branches of quality control. A lot of people see them as being, one or the other, but in most cases, they kind of work together. One of them, do you guys still have a geometric dimensioning and tolerance course, or is it just part of other courses?
That was part of the blueprint.
Or blueprint reading?
Yeah.
So that's one of them, is going from the standard rectangular tolerancing to the geometric dimensioning and tolerance. Thinking like the part and how the part's going to be used rather than just generic, we can be off by this much. The idea of circular tolerances rather than rectangular was a huge, huge upgrade in the industry. It saved on scrap tremendously, just because parts that were thought to have been out of tolerance, now because we're being more honest about the usage and the way it needed to be lined up, actually were acceptable. The other part that it works with is statistical process control. And you'll never see me write that out again, because it's simply known as SPC. Now, statistical process control is the opposite end of geometric dimensioning and tolerancing, or any sort of tolerancing. The tolerancing tells us what we need the part to be. SPC tells us what the process is capable of. So when we do these control charts, and we're not going to get time to get into control charts a whole lot, but when you do control charts and plot stuff on there, the control chart isn't necessarily telling us what we need the parts to be in the finished product. It's telling us this is what the process, we know the process to be capable of doing. So if we're getting out of line with that, we know there's something wrong. We're not necessarily saying the parts are unacceptable, but the parts are out of the normal range of what the process, what we know the process should be doing or has done in the past. So we have a set of data. We end up with what's called a data distribution. Let's say that our data, our variable here, is going to be the length of a part. And let's say we know that our desired length is 82 millimeters. Well, we know that when we go to cut that, of course, you're going to set up a jig of some sort as a stop so that you lay your material in that jig. Saw comes down and cuts it. And you'd think, well, it's going to be exactly the same every time, but it's not. Because when your saw blade comes down and hits that material, when the saw blade makes first contact with the material, it's not uncommon for the saw blade to deflect slightly to one side or another. Now, you can barely see the difference the way I drew it there, but you can see it's slight changes like that. Saw blade hits, and it can slightly deflect off to one side as soon as it hits the material. It could be a bent tooth in the saw that hits. It could be a small imperfection of the surface of the material that pushes it over. But it happens almost every time the saw hits the material. It should be random. If it's always pushing to one side, we know there's a problem with the setup. Maybe our jig got moved and got pushed in closer or further away. Or maybe the teeth on the saw got bent. And so that when they hit, it's always those bent teeth are always pulling the saw off to one side. If that's the case, if it's always to one side, That's what we call assignable cause. And by assignable cause, I mean it's a predictable difference from what we want it to be, or it's called predictable variation from what we want it to be, which means we can find the cause of it and we can fix the cause of it. And it's important not to just adjust. If we're always cutting, half a millimeter short, it's very important not to just adjust the fence by half a millimeter and keep cutting. It's important to figure out what is causing it, like the bent teeth on the blade, because then in a couple of weeks when you replace the blade when it wears out, you got straight teeth on the blade, now you're a half a millimeter off the other direction. So if you figure out what's causing it, it saves you from making mistakes later on. So anyway, it should be equally off to either side, and it should form a data distribution, something like this. If this is the 82 millimeters that we want it to be, if I cut one part, it might be slightly smaller than 82. The next one might be a little bit bigger. The next one might be really close to right on. Maybe a little smaller, a little bigger. And I just keep putting dots on here, the length of those parts that come off. And you can see if I keep doing that, what I get, notice if the two parts are the same length or really close to the same length, I stack the dots up. If I trace a little curve through the top of those points, what I get is a bell curve. We've referred to it as a bell curve, or the actual official name for it, normal curve or normal distribution. It's called the normal distribution because in nature, that is the shape that most sets of data normally take. If we've got that saw set up perfectly, the lengths will vary in a distribution like this. Now the center of that distribution better be at 82 or close to it. This distribution is showing that something in the setup is causing it to cut a little bit large because the center is above 82. So there are two things that can describe our distribution. I have this curve here, and there's 82 is there. I could say the center of that curve is a little less than 82. This green curve, I would say its center is a little more than 82. But they're relatively close to the same shape, as close as I am capable of drawing freehand. If I put in this purple curve, it has the same center as the blue curve. The difference is it's narrower, so it has less spread. So when we describe these distributions, we need to be able to describe the center and the spread. Now the spread is sometimes called So we're going to start, that's what we're going to talk about today, is we're going to talk about measures of center, and if we have time, we'll talk about our measures of dispersion. So I'm going to give us two sets of data here that we're going to look at. Set A, 21, 16, 19, 28, and set B, 13, 25, 31, 19, 26, and 18. Do this one. That should work. Now, the first thing I want to talk about with these is the size. Now these are samples, which means that they are sets of data taken from a larger set of data. Size of a sample is denoted by the letter n. So for set A here, n equals 5 because there's 5 numbers in that list. For set B, n equals 6 because there's 6 numbers in that list. Let's talk about measures of center. Our first real measure of center, our main measure of center, is called the mean. Mean is what most of us to this point in our life have referred to as the average. So this symbol here means sum. Add up all the values. Sum of the x means add up all the values and divide by how many are there. So for set A, 21 plus 16 is 37, plus 19 is 56, plus 28 is 84, plus 21 is 105. By 5 gives us 21. So the mean of set A is 21. Set B, 13 plus 25 is 38, plus 31 is 69, plus 19 is 88, plus 26 is 114, plus 18, 132, divided by 6 is 22, is the center of set B, or is the mean of set B. Hopefully that's one that you're okay with. It's just the average that we've done. Third grade or so. Next is the median, which is physically the middle of the data. The median is a number such that half the data is smaller than it, half the data is larger than it. And it is actually a 3-step process. Step 1 is to put the numbers in order. So for set A, put them in order. What's going to be 16, 19, 21, 21, and 28. So we put them in order. That's step 1. Step 2, find the position of the median. Position is going to be found by taking n times 1/2. Because half the data needs to be smaller, half the data needs to be larger. So here n is 5 times 1/2, 0.5. That decimal, or that number is a decimal. Always round up. Third number in the list is our median. Step 3 is to find the median. 1, 2, 3, 4, 5 are the numbers in the list. The third number is the median. So 21 is the median. Notice that is the same as the median or the mean of that set of numbers. In a well-distributed, normally distributed set of data, the mean and the median should be the same number. Let's do this all for set B. I'll put those in order. I've got what? 13, 18, 19, 25, 26, and 31. Now n equals 6. So 6 times 1/2 is 3. Now this is the reason why I did 2 data sets, because I wanted one of them to be an odd size and the other to be an even size. Since set A was an odd size, we had a decimal when we found that position, so we rounded up. We have a whole number for that position. It is between that place and the next place. So here it'll be between the third and fourth number in the list. What does that mean? 1, 2, 6. Between the third and fourth number, between the 19 and the 25. How do we find what's between them? Well, we add them together and divide by 2. 19 plus 25 is 44, divided by 2. 22 is our median. Again, you notice the median came out to be exactly the same as the mean. I don't usually do that well guessing sets of data, but one of them is at least, 1 or a half off or something. Telling us that both of these sets of data are relatively close. I mean, they're small, so it's hard to say, but they're relatively close to normally distributed. Our third measure of center is the mode. The mode is the number that occurs most often. Well, in set A, that would be the 21. That's the only number that appears more than once, right? See? Set B, there is no mode. There's no number that appears more than once. With small data sets, the mode is kind of pointless. I mean, you can see that for set B, there's no number repeated. And in a small data set, that's very common for that to be the case, that no number is repeated. So there is no mode. Or you can have two numbers that are both repeated a second time. Some textbooks say you can have what they call bimodal. You can have two modes. Some say you can be multimodal. You can have several modes depending on how big it is. For our purposes, there's either one mode or no mode. There isn't one that clearly is more often than the rest. We don't have a mode. Now the mode, as you can see with small data sets, is not very useful. It's really only useful when you're dealing with large numerical sets. I mean, if we have thousands of numbers in the list, then finding the mode might be easier than finding the mean or the median, and it should be the same number anyway. For the other is when we have categorical data. For your purposes, you're pretty much going to be doing numerical data. You're taking a measurement. You're measuring a length, a weight, force that it can handle, a surface hardness, whatever. You're getting a numerical measurement. Categorical data would be if I ask, what's your favorite color? 7. Most people will not respond a number to that. So there's nothing to calculate. You can't find a mean of colors or the median of colors. But you can find a mode. You can find the color that was listed the most often. So I'm guessing your favorite number is blue?
No, that one's orange.
Orange?
Oh.
The final measure of center that we're going to talk about is the mid-range. The mid-range requires us to define a minimum, smallest number in the list, and a maximum, largest number. The mid-range, minimum plus the maximum divided by 2. So for set A, that's 16 plus 28 divided by 2. 16 plus 28 is 44, divided by 2 is 22. Well, the mean and median were 21, so that's actually slightly off. For set B, it's 13 and 31. 13 plus 31 divided by 2. 13 plus 31 is 44, divided by 2 is 22. That's dead on again with the mean and median for that data set. Now, like I said, for a perfectly normally distributed set of data, mean will equal the median. The mid-range is kind of a hack calculation. It's a real quick calculation, not given a lot of importance in. So what that means is curve symmetrical. Or bell curve, and that's symmetrical. Mode is the highest point of the curve because that's the number that occurs the most often. Well, the median, also in the center, half the data is smaller, half the data is larger. And the mean will also be there. The mean, median, and mode are the same number. But we know data can be skewed. Skewed just means it is stretched out in one direction or the other. So I'm exaggerating both of those a little bit. This one over here is called skewed left. Skewed left or lower skewed because it's the lower end, the smaller numbers is where it's stretched out. The left end is where it's stretched out. And this one is called skewed right or upper skewed. Because it's the right side or the higher numbers that are stretched out. And when we do this, the mode is still going to be the highest point on each curve. Now the median has half the numbers smaller and half larger. So the median will move over a little bit. Here it'll move over this way a little bit. And the mean, depending on just how severe the skew is, direction of the skew. So you can always tell what direction the skew is in. Because if the mean is less than the median, that's telling us it's skewed left. Mean is larger than the median, that's telling us we're skewed right. There's some larger numbers in there. The larger numbers occur a little more spread out, stretched out. So the question comes up, what is the better measure of center? What's the best measure of center? I've already kind of ruled out the mid-range as saying it's kind of a hack calculation. And even the mode by saying it's really only useful in special circumstances. So what we're really looking at here is the mean versus the median. Okay, want to put a vote in? Which one do you think is a better measure of center? Most people will say the mean. For one reason we've done it since we were like second or third grade. We're comfortable with it. Second, there's something very satisfying about adding up the numbers and dividing. It's mathematical. You're doing a formula. You're calculating. Whereas the median, you're just putting them in order and finding the middle. That's kind of anticlimactic. But the example I used to illustrate this goes back to 1983, University. And in 1983, the University of Virginia advertised that the average starting salary of a graduate in their BA of Marketing, Bachelor's of Marketing, was just under $78,000. That sounds impressive. If you offered me $78,000 right now, I might be tempted to go. I'm sure any one of you, if you were offered $78,000 for might consider a career in marketing. But to put it in even more perspective, if you go back to 1983, the average high school teacher was starting out between $16,000 and $18,000. So, and that's double. The average high school teacher starts out now between 30 and 35. So that's like making $150,000 a year now. That's $78,000. Pretty good money. Except they failed to disclose in that number one of the graduates that year who did graduate with his degree in marketing, a man by the name of Ralph Sampson. Mr. Sampson was 7 feet 4 inches tall. Both his junior and senior year, he was the NCAA Men's Basketball Player of the Year. But guess where he worked the next year? He was the first pick in the NBA draft for the Houston Rockets. So multi-million-dollar contract. A lot of you probably remember Akeem Olajuwon. I've heard the name Akeem Olajuwon. He was the center for the Houston Rockets for several years. Ralph Sampson was actually drafted by them a couple years before Hakeem Olajuwon, and he was their big player for about 2 years. And when Olajuwon was drafted, Sampson moved to power forward. They called them the Twin Towers. Olajuwon was 7'1", and Sampson was 7'4". Pretty impressive combination in the middle. Although they never won anything. But you can imagine how many $20,000 a year marketing graduates it takes to average that multi-million-dollar salary, $78,000. He was the only one paid over $33,000. Obviously, $78,000 was a the median around $23,000. Marketing is not known as one of your higher paying starting careers. You make money in marketing by getting in a commission position and build up your residual. That 78,000 is a true statistic, but not very descriptive of the data. The term is stability. Median is more stable. Mean can be greatly affected, greatly changed by extreme values. In this case, it was one value that is extremely large compared to the other value, but it could also be extremely small compared to the other value. So the median is often considered to be the better measure of, although, I mean, the two of them work together, mean, median. In a good set of data, they should be really close to the same. Measures of spread. Again, I'm going to come up with a couple of data sets here. I'll call them C so we don't confuse them with A and B. Data set C and D. So data set C, 7, 14, 17, what do I have? Well, we're going to do 7, 8, 20. Need a little bit more. I look at those two data sets. One measure of center, or of spread, I should say. Range. The mid-range was, averaging the minimum and the max. The range is simply the max minus the min. Well, here for data set C, it's 21 minus 7. That's a range of 14. For data set D, it's also 21 minus 7. That's a range of 14. But I would argue that these are not equally spread out. If I do that dot plot, it's a number line, right? I'm going to do set C in red. So I've got a number at 7, 14, 16, 17. I will do D in blue. I've got 7, 7, 9, 18, 20, and 21. I would say the blue ones are more spread out. They're more out to the ends than they are towards the center. But the range doesn't distinguish between them. There's something called standard deviation. And variance that kind of work together. And there's a formula for it, but it's really a 6-step process. Step 1, find the mean. Let's do set C here. 7 plus 14 is 21, plus 16 is 37, plus 17 is 54, plus 21 is 75. For 5 gives us a mean of 15. Step 2, we're going to subtract the mean from each number. So I have my 7, 14, 16, 17, and 21. I'm going to subtract 15 from each. 7 minus 15 is negative 8. 14 minus 15 is negative 1. 16 minus 15 is a positive 1. 17 minus 15 is 2. 21 minus 15 is 4. Minus 15 is 6. These, by the way, are referred to as the deviation. If I add them up, they should equal 0 here. I don't need to add them up for any reason, but that's a good way to double check. Generally, if they're not 0, you screwed up a subtraction like I did there, or your mean is incorrect. Step 3, there. So we have 8 squared. Now remember, when you square a number, any number squared will be positive. If you enter that incorrectly, your calculator is going to try to tell you that that's a negative 8. Remember, when you do it, or negative 64. When you do it, you've got to put it in parentheses. You square negative numbers. Positive 64. Negative 1 squared is positive 1. 1 squared is 1. 2 squared is 4. And 6 squared is 36. Those are the squared deviations. Now, 4. Find the sum. Add those up, in other words. Adds up to 106. That number is referred to as the sum of the squared. Step 5 is the tricky one. Divide by n minus 1. Now, n minus 1 is if this is a sample, and it's almost always going to be a sample. You would never really test every item. Since n equals 5, because there's 5 numbers in the list, n minus 1 equals 5 minus 1, or 4. Divide by 4 to get 26.5. That number there is called the variance. First, the mean squared deviations. Step 6, our final step, is take the square root of the variance. Be careful, this is not squared, this is square root. Square root of 26.5. 5 point something. 5. That. Now, often you hear the term RMS. RMS really is part of this process. RMS deviation is the standard deviation. RMS stands for root of the mean of the squares. Variance is the mean squared deviation. So the RMS deviation is the root of the mean of the squared deviation. In other words, so in SPC, the RMS deviation, that term is often used instead of standard deviation, but they're the same thing. So that standard deviation tells us, on average, the points in that data set are 5.15 away from the average deviation is 5.15. No, it's horrible. I'm actually making you go into the big book. How many still know where your big book is after the last few weeks? Page 662, exercise 32-3. 1 through 6 is really good enough. Actually, 1 through 4 will be good enough. Find the means. And then page 5. Exercise 32-5. Again, I'm just going to have you do 1 through 4. Only find the median and mode. Talk about quartiles. We did not get to quartiles. Now tomorrow, what's going on in class? Well, we'll talk about this junk a little bit more. But I'll let you in on a secret after that.